So I will be talking about today about the runtime verification of communication protocols in Clojure. So at least there is a little bit of Lisp here. So I do a lot of research on static type systems indeed, but I will mostly focus today on a dynamically typed version, right? So that's what the runtime verification is about. And so everything I will talk about today, it's this joint work with two of my master's students who, they have graduated by now. It's Ruben and Erik. And I should especially give credit to Ruben because he's the one that got me hooked on Clojure in the first place, actually. So when he started his graduation project, he came to me and says, okay, I'm interested in your research topic, but I really want to do something with Clojure. I was like, okay, I knew about Clojure, but I had never really used it or anything. But he wanted to do that, and then it turned out that this idea of using Clojure within our research field was actually a great idea, actually, of his. So, and then later, Erik continued this work, and that is what I will talk about today. But before we get into the technical details, let me first say a little bit more about my research background. So I think in general, somehow the long-term research aim is to make concurrent programming easier. So by the time I retire, I hope we fix this at least to some extent. So in general, I work a little bit at the intersection of theory and practice. So on the one hand, we try to develop the theory of static type systems mostly, but we also try to develop tools to also see if these kind of things actually work in practice. Well, to be a little bit more precise, because I suppose concurrent programming means many things to many different people, I'd like to be bound to the scope for this presentation a little bit. So we'll be looking at shared memory concurrency, okay, but with a little bit of a twist. And the twist here is that we assume that in this programming language that we are using for shared memory, we're going to have message passing as a kind of abstraction on top of shared memory. Okay, so I will use message passing, but it is not about distributed computing at all. It is just that you use channels in your shared memory concurrent software, hopefully to make programming a little bit easier. And I would say that the premier example of a language that sort of popularized this is Go. Right? In Go, you have this very primacy of channel-based communication between lightweight threads. Okay, I think more or other modern programming languages have developed this as well by now, including Clojure. Right? But I will say a little bit more about that. And I think for at least some time, the idea was that message passing would make our lives simpler. But I think by now we also have seen at least a number of scientific studies that show that message passing compared to classical synchronization rules in logs and so on, it's not really less error prone, right? You make different kinds of mistakes, but you still make mistakes. And so we need to have some kind of programming language support for this as well. And one particular property that I'm interested in to help programmers establish is protocol compliance. So the idea is that you have, you write your implementation of your concurrent program, and you have these threads that send and receive messages to and from each other. But when you do this, in some sense, you have intuitively some communication protocol in mind, right? And you want to know whether or not this implementation actually satisfies this intention that you have. And this is kind of complicated to do, and I will show you on the next slide. Okay, so this was just a few keywords, so to speak, to set the expectations for the rest of the talk, and I will hopefully clarify it in the rest of the time. Okay, so more concretely, what is let's say the challenge that I want to help programmers with? So imagine that we have this, or that we need to implement this concurrent program. And I will assume that we have a specification S and an implementation I. And this specification S, it consists of 3 elements, is my assumption. First, I need to know something about which threads I have in the system, and I will just call them Alice, Bob, and Carol in the rest of this presentation. Then, we assume that each of these threads, even though at the hardware level, so to speak, we have shared memory, they're going to use their memory in kind of a disciplined way, such that from the, let's say, programming perspective, it has to be private, right? It has to be isolated. And so when they want to communicate data with each other, we'll assume that we have a bunch of channels. And I'm not going to make any assumptions on the particular topology of the network. So it could be a complete thing, it could be a more partial thing, like you see here on the slide. That doesn't really matter. And so this threads into channels, the sort of the structural aspects of the specification. But of course, I also need to know something about the intended behavior of these threads. And so I'll also assume that we have somehow a protocol specification that tells us what is the communication behavior that the threads should engage in, right? So here in this example, we could have a piece of natural language where we say, well, Alice first needs to send a number to Bob, and then Bob sends another number either to Carol or to Dave, etc., right? And so at this point, I'm not going to make any assumptions on what kind of, the format in which the specification exists. So it could be natural language, or it could be something semi-formal like a sequence diagram, or perhaps even actual formal specification. But my claim is that at least such a specification exists somewhere, right? It could be, actually on paper, but also just, inside of the mind of the programmer. He needs to know something about, what he intends to program. Okay. So, assuming that we have such a specification and an implementation, then I think one of the key challenges is to ensure that this implementation is safe and live relative to the specification. And these notions of safety and liveness, they're essentially just the classical notions of safety and liveness that you might have heard about in verification theory. So safety here would mean that bad channel actions never happen, where bad is defined relative to your specification. Okay, so for instance, a bad channel action to start with would be when Alice sends a Boolean to Bob. Right, this is not allowed by the specification, so that's something that we want to avoid. And liveness means that good channel actions eventually happen. And so, more precisely, when I talk about liveness, it essentially means that we have a kind of deadlock freedom. So, at any point during the execution, either all the threads have already successfully terminated, or there is at least one thread that can make progress, right? Send the next message or receive the next message. That's my notion of liveness here today. And my claim is that, reasoning about these kinds of properties is not that simple at all. And I want to illustrate it by means of a simple example. So let's try to do two things. First, let's try to write a more kind of a formal specification for the protocol that I've seen here, that I show you on the top. And this is basically to introduce, the main notation that I will use throughout the presentation. And I will represent these specifications like this. And when you squint your eyes a little bit, it's essentially just regular expressions where the atoms are communications, right? So we have sequential composition, and we have choice, and then the atoms that we see here, there are 3 atoms here, they represent atomic communications, right? So here, A arrow B colon that means a number is communicated from Alice to Bob, right? And so after this, we have a choice between a number being communicated from Bob to Carol or from Bob to Dave, right? So that's exactly the same as what we have here in natural language. So this is my specification, and now I want to show you 3 implementations. And the first implementation looks something like this. So the first thing that we do in this implementation is actually create this communication infrastructure, right? So the channels. And I'll call these channels X, Y, and Z in this picture. And so in the code here that I show, we bind 3 new channels, 3 fresh channels to variables X, Y, and Z. So this function chan, it basically creates a new channel, allocates it on the heap, and returns a reference to the channel. And the argument of this chan function is the capacity of the buffer. Okay, so these channels, we assume that they are asynchronous, right? So this, after you do a send, you can immediately proceed, and the receive operation will happen somewhat later in time. And in the meantime, the messages that you send through the channel are stored in a buffer, and the capacity of the buffer is here 1. So it can contain 1 message in this example. This notation, by the way, that I use here, it is almost like Clojure, but not exactly. So I abstracted away some of the details that don't matter so much. We will see the actual Clojure code later on in the presentation. Okay, so this is just to create this infrastructure, and then the only thing we need to do, of course, is to define the actual threads, and it will, in this notation, again, it looks something like this. So I'd first like to draw your attention to this double bar operators, which is parallel composition. Okay, so on every side of each of those double bars, you have the definition of 1 thread. Okay, and more precisely, I can sort of map these pieces of code to the process, to the threads that I have here in my picture. So For Alice, the implementation is just to send value 5 through channel X, right? For Carol, the implementation is to receive through channel Y. For Dave, we have the nil thread, which doesn't do anything at all and just immediately terminates. And Bob is the most complicated thread. He first receives through channel X, then checks if the value is odd. If it is odd, then he sends value 6 through channel Y, and otherwise he sends true through channel Z. Okay? And so now the question is this implementation safe and live relative to this specification? Okay? And to answer this question, essentially what you need to do as a programmer is reconstruct all the executions that this implementation might engage in. Right? So we can do that here. And the first observation that we need to make is that Carol and Dave and also Bob, they cannot start, right? Because, well, Dave doesn't do anything, so obviously, but Carol and Bob, yeah, they start with the receive. And initially there's nothing in the buffer, so you cannot start by just the receive. So this means that Alice needs to first start by sending, right, value 5 through channel X. And after this has happened, then of course Bob can also receive through X, and he will receive 5. And 5 is an odd number, okay? So he will enter his then branch, send 6 through channel Y, and at that point, Carol can receive through channel Y value 6. And after Carol has received, then we have reached full termination of all the threads, right? So then the whole program, the whole implementation is done. And so we can now make two observations, I would say. So first, we can say, okay, this is actually a safe execution because we start here with the communication of a number through channel X, and the sender is Alice and the receiver is Bob, so that is exactly in compliance with the specification that I have here. And subsequently, we have the communication of another number through channel Y from Bob to Carol, which is again in compliance with the specification. So here, safety is okay. And also, by the time that Carol receives through Y, or after she has done that, all the threads have terminated. Right, so we can also say, okay, this is also live. So we are quite happy because this implementation is indeed safe and live. But I would say that this implementation, it still looks a bit weird because, Dave here does nothing. That doesn't make a lot of sense. So it would perhaps be more natural to say, well, okay, maybe Dave wants to try to receive through this channel Z because, Dave doesn't know how Bob is going to make the choice. So we can try to change this implementation into a slight variation where we have a receive through channel Z at Dave. And our first observation now should be that regarding safety, this doesn't make any difference, right? Because Alice, Bob, and Carol, this execution involved actually only them, right? So whatever we put here for Dave, it doesn't matter. But liveness is no longer guaranteed, right? Because by the time, yes?
I have a slight question. A small question. What would happen if you replace the send x5 by send x4?
Yes. Are these questions audible through or do I need to repeat them?
We can give
Repeat them, yes. Okay, so the question is, what happens if I replace 5 with 4? And that's my next slide. So I will get there. Thank you. But first, to finish this slide, it's that, okay, so safety is still fine, but by the time that Alice, Bob, and Carol terminate, Bob is, who's this? Dave. Dave is still trying to receive something, right? So Dave now gets stuck in a local deadlock, so to speak, and that is something that we want to avoid because it prevents termination of the whole application. Now, we can again change this implementation a little bit and, answer the question that was just asked. What happens if we would, let Alice send value 4? Now in this situation, I will also just replace here Carol with the empty thread because this will allow us to at least get liveness. But if we now reconstruct our execution, what happens is that, so Bob will now receive 4, of course. 4 is not an odd number, so he will send true through channel Z. Dave is expecting to receive a value, so he will receive true, which is perfectly fine. And so after the receive, Alice, Bob, Carol, and Dave, they have all successfully terminated. So liveness here is okay, but this communication, right, of a Boolean from Bob to Dave, right, that is not compliant with the protocol, right, because Bob is allowed to send a message, but if he sends a message, then it has to be a number. Okay, so here we would say that this implementation is live, but it's not safe. Now, if anything, spending 5, 6, or 7 minutes perhaps even on these examples should illustrate that this is tedious, boring, and error-prone, and we don't want to expose programmers to this, right? They should have better support in the language actually to do this kind of reasoning for you. And so within my research field, within my research community, many people are looking at alternative methods and techniques and tools basically to provide automated support in which this style of reasoning can be mechanized. And so one of these approaches is called multi-party session types. Okay, this was invented maybe 15 years ago or so. And at least from a scientific perspective, I think multi-party session types, or MPST as I will often abbreviate it, has been quite successful, right? It has made a lot of scientific impact. The practical impact, however, has been perhaps, especially when you compare it to the scientific impact, has been a bit underwhelming, perhaps. And the reason for this I will come to on the next slide, or at least why I believe that this is the case. But let me first try to explain on one slide what this multi-party session types actually is. And this is, I think maybe the only slide about static type system in the whole presentation. So please bear with me. Okay, so the idea is we still have this implementation. It consists, in this case, of 3 threads, because otherwise it doesn't fit on my slide. So we just have Alice, Bob, and Carol in this case. And the idea is still also that we have this specification. Okay, and so what we want to do is somehow automatically prove that these implementations comply with this specification. And we do so in 2 steps using MPST method. The first step is to decompose this specification into a bunch of local specifications. Okay, and the idea of these local specifications is that that each of them sort of isolates the intended communication behavior for one of the threads. Right? So you can think of this global specification as like like a sequence diagram, right? And these local specifications, each of them would be one of the lifelines in your sequence diagram, right? So you isolate the behavior for one thread. And if we continue our example of the previous slide, then these local specifications, they look something like this. Okay, so the local specification for Alice is B !nat, which means a number is sent to Bob. Okay, so exclamation mark is the send operation. And for Bob, for instance, we have A !nat, where question mark represents a receive operation. So this means a number is received from Alice, and subsequently, right, so we still have this kind of regular expression notation. A number is communicated to Carol or to Dave. Okay, and for Carol, we have that she either receives a number from Bob or she immediately terminates. Okay, so 1 here is a special constant to represent successful termination. And so, well, if we would really continue this example, we would have something similar also for Dave. Okay, and so after this decomposition step, we get these 3 things. Okay, and then the second step of this methodology is to now individually type check each of those threads implementations against its own local specification. Okay, now there are also other kinds of techniques, analysis techniques that you could use here, like simulation relations or maybe some kind of model checking. But in multi-party session typing, you try to do it with type checking. And this type checking procedure is basically, well, it's a syntactic procedure, right? So you sort of compare the structure of the implementations against the structures of the specifications. So for instance, here we would say that the implementation of Alice, right, sending 5 through X, if we assume that X is actually a channel from Alice to Bob, then this send operation indeed complies with the specification that we have here. Right? And you can, in the same way, you can do that for Bob and for Carol. And then hopefully each of your threads is individually well typed against its own local specification. And this individual well typedness is very important because the main theorem of multi-party session types is that if each of these threads is indeed individually well typed, statically at compile time, then at runtime you get safety and liveness of the parallel composition. Okay, so I would say that this is quite of a strong correctness guarantee that you get by doing compile time analysis, and this is also what got many people in my community at least excited about this, the potential of this method. The only problem is that it's not really expressive. Not really expressive in the sense that there are many pairs of a specification and an implementation for which somehow this method is not applicable. And the reason that it is not applicable is in general because this, this static type checking, as you probably well know, is conservative, right? So it will reject many implementations that are actually fine, but for which the static type checker is just unable to prove it. And to be a little bit more precise, the two main reasons why we have this limited expressiveness, they really are related to these two main steps of decomposition and type checking. So for decomposition, right, intuitively, when we decompose something, we want to have some kind of relation between the decomposition and the thing that we started with, right? We want it somehow to preserve the semantics or the behavior of this original specification. But it turns out that in many cases, we cannot do this. And this is for two reasons. First of all, in some cases, it's simply impossible to find a behavior-preserving decomposition, right? But in other cases, such a decomposition actually would exist, but our algorithms are not smart enough to find it, right? And so an example of a situation where this decomposition fails is actually the example that we saw here already on the slide. So I don't want to go into the details, but if you would really associate formal semantics with parallel compositions of such local specifications, so you try to recompose them into the global specification, then you get something different from the global specification that we started with. And so from a practical perspective, what would happen is that you give this global specification to a tool, right, one of our MPST tools, and this tool will then say, yeah, okay, I can compute this decomposition for Alice and for Bob, but for Carol, no, I'm just going to fail. And intuitively, the problem here is that Alice, using this kind of notation, Carol makes the choice between receiving a number or immediately terminating. But this is not really Carol's choice to make, right? It's Bob's choice. But yeah, Carol cannot know if she will in the future still receive this message from Bob or whether Bob has chosen to send the message to Dave, right? So that's intuitively the issue. And so, in this case, actually such a decomposition does not exist. So in general, many specifications cannot be decomposed modulo some kind of equivalence relation. Okay, so that's one issue. Now, even if this issue is circumvented somehow, if you have a specification for which you can have such a behavior-preserving decomposition, then there is another issue, and this other issue is related to the type checking, because the type checking itself is, as usual with static type systems, also conservative. And the main source of conservatism here in this particular context is related to conditional choices. Okay, so with these conditional choices, statically we don't know yet, of course, if you take the then branch or if you take the else branch. And so if we want to know that this whole conditional choice is compliant with the protocol, we need to check this for both of the branches, right? So we need to check that both of the branches are safe and live relative to the specification. Then you can run into the situation, actually like in this example that we have here, that one of the branches does comply with the protocol, but the other branch doesn't. And then, if at runtime you would never get in the incompliant branch, you're actually rejecting this program, even though you don't have to do that. And that's the same here actually. So I'm pretending here as if this would actually be well typed, but if you would really give this to our type checker, it would say no, right? Because the branch where you have where Alice sends 4, like one of the questions before, it doesn't comply with the protocol. And so, in general, many implementations cannot actually be type checked. I would say that a very big portion of the research in this area has the objective to try to improve expressiveness. And also myself, I think I spent or wasted, depending on what perspective you take, many years of my life on trying to reach this objective. And at some point when I was doing this, I thought, the progress that we make here is, I wouldn't say incremental, but it's sort of step by step. And at some point I thought, okay, so what would be the most extreme thing that we could try to do to improve this kind of expressiveness? And so then you can take a look at this picture, and if you want to do the most extreme thing, so to speak, then you can say, if this decomposition, if that is an issue, then maybe you can just remove this decomposition altogether, because then you also don't have the issue anymore. And similarly, if type checking is an issue, static type checking at compile time, then maybe you shouldn't do anything at compile time and just remove this type checks. And if you remove that, then maybe, these local specifications, I don't know, you don't need them anymore. So then you just get this picture. And then we're back at where we started, and then you can say, yeah, okay, so if you want to do nothing at compile time, yeah, what else can we do? And then I sat and I thought, okay, so we tried to do all the analysis at runtime. Okay, so that at some point was our idea. But then at the time, I mean, we didn't have the resources, we didn't have, the actual good ideas, so to speak, to actually manage this. So it spent some time in the back of my mind until my student Ruben came along and he said, okay, I want to do something in Clojure. And then I looked at Clojure, right, for the first time in detail, and then I realized, okay, but Clojure is maybe the perfect programming language in which we can try to prototype this kind of runtime verification. Okay, and that's what I want to talk about in the rest of this presentation. Okay, but before I want to go actually to the Clojure part, let me first, at a slightly higher level, try to explain what is the kind of runtime verification that we want to do. So the idea is that we still have this implementation and still have the specification, but when we execute this implementation at runtime, we're going to add two components to the system that we usually have. So the first component is what I'll call the instrumentation. And this instrumentation is basically a very thin layer around the original implementation that allows us to dynamically, so at runtime, observe every send and receive operation that happens. Okay, so you can think of it as kind of a logger or something, a runtime logger. So that's the first component that we add. And the second component we add is what is called the monitor. And this monitor will actually, check for us whether the send and receive operations that we observe through the instrumentation are safe and live relative to the specification. Okay, and so this monitor, you can think of it as really a kind of runtime component, something that actually runs alongside the implementation, but it also has access to the specification. That's really important because it needs to know what is the intended behavior of the application. And so this, when you execute this, it would look something like this. So maybe we just start running these things, and at some point, Alice maybe performs a send operation. And so the instrumentation is now capable of sort of sensing this, and right before the actual send operation happens, so before it takes effect, before you actually put this value 4 inside the buffer, the instrumentation intervenes. It suspends temporarily Alice. Okay, and it first asks the monitor, is this send operation actually allowed by the specification? So the monitor receives this question or this request, and it has access to this specification, and then it can see, yeah, okay, I mean, the first action from Alice to Bob, it's the send of a number, and this is the number, so this is okay. So it sort of approves or it certifies this action, and it confirms to the instrumentation that everything is fine. And so at this point, the instrumentation will resume Alice, and only then will the send actually take place. Right? So then the value is put into the channel, and everybody's happy, right? Everything is fine. So then maybe some time later, Bob performs the corresponding receive operation, and the same thing happens. So the instrumentation sort of picks it up, suspends Bob, asks the monitor if this is okay. The monitor checks the updated specification, right? Because we now need to know that this first send operation has already happened. So you can think of this specification actually as a kind of a state machine. And when you look at our code, it actually is interpreted as a state machine. The monitor looks at this updated specification, sees that the receive is indeed also allowed, indeed confirms it again to the implementation, and everybody is happy again. And Bob proceeds. But Bob now received this non-odd number, an even number, and so he, if we continue our example, will now send a Boolean to Carol, right? So the instrumentation will again sort of pick this up and ask the monitor, is Bob allowed to send true to Carol at this point, or to Dave at this point, excuse me, to Dave. And now at this point, the monitor will say, no, I mean, look at this specification. Bob is allowed to send something to Dave, but it has to be a number and not a Boolean. And so now he will say, okay, this is something that Bob is not supposed to do. And so before the instrumentation, or before Bob is actually able to send this wrong value, this wrongly typed value, the instrumentation will now throw an exception, a runtime error, inside Bob to prevent it from actually doing this. And so this unsafe action, or this Boolean value, will never be actually put inside the channel. In principle, Alice and Carol, they can still continue with their own execution, so we don't necessarily terminate or throw an exception in the entire application. And sometimes this is useful. In this example, it's not, but it could be useful. So this is the general approach, and using this approach, I hope it is fairly simple to see that safety is very easily guaranteed because, well, we basically check every communication action right before it happens, and if it is not allowed, then we throw this exception so it doesn't really happen. So that's okay. For liveness, we have kind of an experimental deadlock checker. So we do some bookkeeping to keep track of which threads are waiting to receive something or waiting to send something in case the buffer of the channel is already full. And then based on this kind of bookkeeping, we can throw exceptions if there is a global deadlock for all the remaining processes. But it's a bit more experimental in the sense that we also don't have a very clear theoretical understanding yet of what kind of guarantees we precisely can give with this technique. So this is something that we're still studying. Okay. So in the rest of the talk, how am I doing for time actually?
35 minutes in?
You have another
35 minutes. Okay, good, cool. Cool. So in the rest of the talk, I now want to go a little bit more into the Clojure code, and I want to show you mainly just one simple example to show you from the programmer's perspective how you could use this kind of runtime verification. But before that, I thought it would also be interesting maybe to clarify a bit more why Clojure is such a perfect language to do this kind of research for. And I think that there are 5 reasons, 3 of which are technical and 2 of which are actually less technical or non-technical even, why Clojure would be the perfect research vehicle for this kind of techniques. And so the first technical reason is that the concurrency model of Clojure fits very well the concurrency model of session types. So under the hood, of course, you have just shared memory in Clojure, and you can even escape to Java and so on. But regarding the concurrency model, you have this standard library where you have channels and message passing and the ability to spawn threads and so on. So this very nicely matches the theoretical models and assumptions that we usually work with. Furthermore, Clojure is of course dynamically typed, and this seems to fit very well this idea of runtime verification. And I've been calling it runtime verification throughout the whole presentation, but actually in the papers that we write about this, we don't call it runtime verification so much, but more dynamic type checking actually, right? So the idea was that we can sort of integrate this nicely with the dynamic type checking that Clojure already does for data types. And the third reason why this was a good fit is because, of course, your Clojure, like all Lisps, has a very powerful macro system, and this enabled us to implement the specification language basically as just Clojure macros. And this might sound very intuitive or obvious to you, but at the time that we started doing this, the only specification languages that we had for session types were all external DSLs. Right, so if you wanted to use them, you need to install separate tools and a separate compiler, and it was very disruptive to the normal programming workflow that people have, I suppose. Whereas here, we could sort of try to get a more seamless experience of expressing your protocols and writing your implementations all in the same mainstream language. Okay, so these are 3 important technical reasons. Then there are also some more cultural reasons, perhaps. The first one being that in the annual Clojure survey, which has been running for, I don't know, 6 or 7 or maybe 8 years now, developers consistently indicate that ease of development is more important to them than runtime performance. And this is important for this kind of technology because, inescapably, when you do start doing things dynamically, we are going to impose some performance penalties also on the runtimes. And so we were hoping that a community that values ease of development, that values ease of development would be more, let's say, tolerant, so to speak, to these kinds of runtime overheads than, for instance, if you are an embedded programmer or a systems programmer. And finally, perhaps the least important one, but still a little bit important, I would say, it is by now the 3rd most loved language in the Stack Overflow developer survey, which was, when we started doing this work, it was maybe the 6th or the 7th, so it's even increasing in popularity in that sense. Which is interesting because, well, surely Clojure is no longer the niche language that it once used to be, right? And so for this kind of research, we always try to do it for a mainstream language, right, or a sufficiently mainstream language, so that we can also, try to hope that we have some practical impact as well. And so, yeah, I think this was at least to some extent important. Okay, so let me now show you just an example of what it looks like in practice, and I want to do it with a very simple, simple example. It's just tic-tac-toe, which I'm going to assume that all of us have seen or played at least once in our lives. So I want to show you the specification and the implementation, but before I get to the code, let me first give you an impression of how I think this program is going to execute in a more visual style. So we'll have two threads, the players, Alice and Bob, and we have two channels between them so that they can actually communicate. And then each of these two threads is going to have its own local copy of the game board. Okay? And so what happens then at runtime is that Alice goes first, and she puts her token in some place of the grid, and then she sends information about this move, right? So the grid location sends it to Bob. Bob receives this, updates its own grid accordingly, and then makes his own move and sends information back to Alice. And then Alice and Bob they take turns to play this game until at some point Alice makes her final move, and now she knows that she's the winner. But she still needs to communicate this information to Bob, of course. And once Bob has processed this, Bob also knows that he is the loser. And so the game is over, and Alice and Bob, they can both close their channels. Okay, so in Clojure, you need to close the channels so that the JVM can reclaim the memory and so on. So this is what we're going to specify and implement on this slide and the next. And so I want to start with the specification. And it looks something like this. So first, we need to define or declare the threads in some sense. So I will use the role function here, and the idea is that the actual threads that we have in the implementation, they enact or they play a certain role, namely that of Alice or that of Bob. Okay. The rest of the specification I will give you in two parts. So the first, what I want to show you is kind of an auxiliary specification that looks something like this. So this is just a part of the specification that governs the closing of the channels. So we have this DSL keyword just to indicate that the rest of the code that follows is part of this DSL. Then we have these three hashes, A, B, which represents the closing of the channel from A to B, and symmetrically this is the closing of the channel from B to A. And bar here means that the actions that are specified in the arguments, that they can happen in any order. Okay, so basically this just means that the channels are closed and we don't care about who of the two, whether Alice or Bob goes first. Okay, so this is like an auxiliary specification. And then the whole specification looks something like this. Okay, so the general anatomy is the same as before. So we have the name of the specification, we have this DSL keyword. Then we declare somehow a kind of a loop. So fix, it would stand for a little bit for fixed point. So we calculate some kind of fixed point, but the details don't matter so much. You can think of it as just recursion, where x is the recursion variable. And so at the end of the loop, we make the recursive call. Okay, that's fine. But what happens inside of this, inside the body, is that we have between the square brackets is just a sequence of things that needs to happen or that can happen. Where the first thing with this arrow is the communication. So this is a communication from Alice to Bob of type long, which is just a number on the JVM. And after this communication, there is a choice. So we have two alternatives. Either we insert an instance of this auxiliary specification, so the channels can be closed, or we continue with another communication from Bob to Alice. Okay. And so what this then essentially means is that the specification is states that you have this alternating sequence of communications between Alice and Bob and from Bob to Alice. And after each of such a communication, you can always decide to close the channels and terminate. Okay?
Excuse me.
Yes?
Par sounds like parallel, but you said that it can happen in any order. So do you mean it still needs to be sequential, but the order is not important? Or can it really happen in parallel?
It means
Can
that
you repeat the question?
it is concurrent. So we have the interleaving.
Okay.
Yes? Okay. Yes, so, okay, so, well, to answer the question in a bit more, maybe I should repeat the question. So the question, so the question was, what is exactly the semantics of parallel, right? If things can really happen in parallel, or whether we do some kind of linearization essentially. And the answer is we do, oh, I have so many slides, right? We do a kind of linearization because the monitor can process only one action at a time. So we need to say that, always say first you close this and then you close that, or in the other way around. Okay, right, okay, but this was the specification. Okay, so now let's have a look at the Clojure code for the implementation. First, here are just some general tic-tac-toe game concepts. So, for instance, we have G0, which is just the initial grid where all the spaces are blank. You know, this is just a list of 9 items, essentially. Then we have some functions to get a random blank space on the grid. We have a function to change the grid, so you can put our own, we can put a token on one of the, grid location I. We can check if the grid is not final, and then there's some more. But the details don't matter so much. Next, we need to load the standard library of Clojure that contains all the channels and the message passing and the threads and so on. And it's called Clojure Core Async. Okay, so we just load it. And then we can construct the 2 channels. C1 is supposed to be from Alice to Bob, C2 from Bob to Alice. You see that this notation for channels is the same as what we had earlier on in the presentation. And then finally what we need to do is we need to define the actual threads. And it will look something like this. So in Clojure you have this thread macro which spawns a thread, and it will execute all the code that is passed as an argument. And we already know, of course, that at the end of this thread execution we want to close the channel. Okay, so that's one thing. The only thing that we need to fill now is the actual game loop, sort of, that the thread engages in. And so it will look like this. We actually have this loop, which is just Clojure code. And the loop is parameterized by G, and initially the value of G is the initial grid, right? So this G is just the current state of the game from the local perspective, so to speak. So then the first thing that Alice does is she tries to find a blank space, a random blank space on the current grid, and I is the index of this space. Then she updates her own grid accordingly and rebinds it to a variable G. Then she sends information about this move, right? So the index of this previously blank space, she sends it to Bob through channel C1, and this function symbol here is the send operation in Clojure. Then she checks if the grid is not final. If it is final, then okay, she just exits the loop and she closes the channel. But if it is not final, then you know the game is still going on, and she expects to receive another value from Bob, right? And this is this function symbol is the receive operation in Clojure. Then you update the grid accordingly. Again, you check if the grid is not final, and you keep playing this game until everything is finished. So this is what Alice does, and what Bob does is just symmetric. Okay, so let's not go into those details. And this is all just, let's say, pure Clojure code. So you could copy paste this in the REPL and then execute it, and you know you would simulate a game of tic-tac-toe. But if you also want to have additional, like say, safety and liveness assurances, you could deploy sort of our runtime verifier. And to do that, you need to do the following. So first, instead of loading the standard library of Clojure, you need to load our own library. Okay, that's fine. Then, when you have done this, we give you functions to actually construct the monitor for the specification that we wrote on the previous page. Okay. To actually also sort of configure the instrumentation, we also require you to say for each of the channels who are the intended sender, receiver, and which monitor you will be using to do the actual verification. And so once you have added all this, the remaining things that you need to change is nothing. So, right, so this is actually all the changes that you need to make, and in particular the code of the threads can remain exactly the same. So we hope that this is, well, we believe that this is kind of non-invasive to start using this kind of technology. You just need to add a little bit of extra information in the configuration, really, of your communication network. That's the idea. And so then you can, again, run this program for the second time, and then actually, to our surprise as well, there was an unsafe execution that we found in this way. So I don't want to go into the details here. It's a little bit of a technical thing, but yeah, so we made a mistake actually somewhere. But we didn't anticipate it. So, Okay, so just to show you, give you a few more, a little bit of a taste of the things that we can specify in this way is, well, what in our community is called indexed roles and parameterized specifications, but it basically just means that we can have these kinds of communication topologies where the number of threads is known only at runtime instead of at compile time. And this is typically something that our static type systems can deal with very poorly, right? But now that we have the runtime verifier, we can actually support these kinds of things. So we can have, in this case, this would be a ring where you have a variable number of threads, and we can also have other kinds of networks and so on. But the details are not so very important, but I just wanted to show you that we have this kind of parametrization as well. Okay, so if I would be a salesperson and I would try to sell all this to some, I don't know, a paying customer perhaps, then I would say, yeah, okay. So what are the nice things are that we get these the safety guarantees, right? So if a send or a receive happens, then it is really allowed. You also have liveness, although it's a bit more experimental. And also, which I should also mention, is that we have freedom of data races. But this is not something that I can take credit for actually, because it is somehow, it comes out of the box if you use pure Clojure. Because in Clojure, all the data structures are immutable by default. So if you stick to pure Clojure, you also cannot have data races, which makes, I think, this runtime verification approach very nicely complementary to what you already have in Clojure. And I would also say something about the ergonomics, right? So our specification language is more expressive than what you have in the classical MPST approaches. Because we are using an embedded DSL, the syntax of our specification language is somehow a subset of Clojure, so you don't need to learn new things in that respect. You can also just continue to use the existing tools that you already have. So starting to use this kind of stuff should be, at least that's the intention, non-invasive. Okay. Okay, so that's all very nice, but the thing that I am trying to, well, that I have not discussed so far yet, perhaps suspiciously, is the performance. Okay, because we are going to do all these kinds of extra checks at runtime, and so yeah, this could be a lot in principle, of course. So yeah, what about performance? And so to investigate this performance, we did a bunch of benchmarks from a third-party benchmarking suite, and it's called the NAS parallel benchmarks. And so these benchmarks, they are from computational fluid dynamics. Now I know close to nothing about computational fluid dynamics, but that's not really important. It doesn't really matter what these things compute. It's more about, for us at least, the communication structures and patterns that they engage in. And so what we did is we took the reference implementations, which are written in Java, and then we, well, basically we removed all the Java-based communication code and we replaced it with Clojure-based communication code because, well, Clojure also runs on the JVM, so there's very nice interoperability between, well, Java and Clojure. And then we ran our versions also with the runtime verifier. And so we did this on, well, at least at the time it was a sizable multi-core machine. And then we got the following results. Okay, so on the horizontal axis you see the number of threads, right? So we also wanted to have an idea of scalability. And on the vertical axis you see our slowdown, so to speak. Okay, and I think there are two main takeaway messages here. So first, if you look at these charts in the middle, then what we see is that the overhead, it can actually be less than 5%. And we were quite surprised to see that because it was much better than we had dare to hope for, actually. And so if the overhead indeed is less than 5%, then I think that you can even use this kind of technology as a fail-safe in production, right? Because 5% is really not that bad. However, we also need to, acknowledge somehow the charts on the sides, where in these applications we get slowdowns of 4 to 5 times. Okay, and 4 to 5 times, I think it is, way too much to run this in a production environment. But still, it could be useful in the testing and debugging phase during the development, right? In the same way that people use memory profilers that also, slow down your program to an order of magnitude. But it's still very useful to catch bugs. So that would be the second kind of use case. Okay, then I also had a few slides about the mathematical details. So we also formalized all of this stuff in mathematical theory. but I'm going to skip that in view of time, I think, and also because it's Monday morning. Yeah, okay. So the takeaways. I focused mostly on the engineering side in this presentation, but there's also, well, being a static type systems person in the end, there's also some formal stuff and things. But yeah, I will just show you some formulas here, but I will skip it right now. Okay. Well, very complicated. Okay, so that is all I wanted to say today, I think. Yes, so this is the link to our GitHub page. There's also some references to the papers if you're interested. I think this is where I will stop. Thank you very much for your attention.
Okay, so thank you very much. I think we have time for a few questions. Yes?
Do you plan to use some kind of type inference to evade some runtime checks?
Okay, yes, thank you. So the question is if we want to use type inference to avoid some of the runtime checks, right?
Yes.
Yes, so we are currently looking at a kind of gradual typing, actually. So I think it would not really be inference, so we would still ask the programmer to write the specification, but he needs to do that anyway, I would say. But then at least, indeed, some of the checks we want to try to do statically at compile time already. Let's say the simple checks, so that at runtime we can avoid the extra overhead that those checks would otherwise impose. Yes, thank you. Yeah.
Your users, you didn't talk about how many users you have, but the Clojure programmers, which type of IDE are they using? Are they using the Emacs-based one or the IntelliJ-based one?
The short answer is I don't know. Sorry, I need to repeat the question. Okay, so the question is, what kind of IDE do Clojure programmers typically use? And the short answer is I don't know. But I think it is one of the questions in the annual Clojure survey, so we should be able to get it rather precise.
If I can explain why I asked the question, is because introducing new Clojure programmers who don't want to use Emacs, there's this very beautiful IDE in IntelliJ, but it performs very poorly with macros. And a central part of your system seems to be macros. My question is, does it work in the IntelliJ system?
Okay, yes. So surely it works in the So the question is, Emacs works poorly with macros, but IntelliJ works opposite. Emacs works very well with macros. IntelliJ does not work with macros at all, sort of, roughly. These are not my words. No. I'm just repeating the question. No. So and the question is, does our system work with IntelliJ? And the answer is yes. So we develop. So my students and myself, we work only in IntelliJ actually. So it will work even better in Emacs, I would say. Yes.
Yeah. So this is something you glossed over in your presentation, but you just said really quickly that the tic-tac-toe implementation you wrote was actually tripped up your verifier.
Yeah.
But I don't know, is that because the implementation was, I also would think looking at the implementation, that seems fine. Yes. So was that a problem with the, it wasn't clear to me whether that was a problem with your verifier or that was actually a problem with the implementation, I don't know, I think that's interesting. Could you actually go more into detail?
Yes, okay, so the question is, in this tic-tac-toe example, we found, or we had a safety violation when we run the thing, and the question is this a problem with the implementation or with the verifier? And the answer is neither, because it was a problem with the specification, actually. So the specification, the problem is that because we do asynchronous, well, maybe I can show it. So what could happen is that So what could So what could happen is that when Alice and Bob close the channel, so it's about the timing of closing the channels. Alice can close her channel. Maybe I should even do it like this. So at this point, Alice has sent her last value to Bob, right? And what could happen now is that Alice immediately closes her channel before Bob has received this value. And this should be allowed, but in the specification that I showed you, actually it's not. It's not, because we say that this communication needs to have happened before we continue with the closing of the channel.
So do you have a way to fix the specification?
Yes, well, by now we do, yes.
Okay.
Yes. Yes.
I have a question. Have you tried this system on some complex program or system that you wanted to prove or something like production level, or is still for now it's just an academic exercise?
So the question is this an academic exercise or is it serious? but phrase it in a more polite fashion, yes. No, thank you. I would say it is pretty much an academic exercise. I think the most complex things that we have done is certain classes of distributed algorithms that we have tried. But I mean, I would still say that these implementations are not production level implementations. But for us, it was, I mean, the goal of the research goal of all this is to see if we can at least improve the expressiveness of this kind of technology. And so I think in that goal we sort of succeeded, but to make actually the step to go to a production level implementation as well, I think that would be, yeah, it would require a lot more engineering effort as well, yes.
I'm sorry, but I must come back to my question. Can you please show the first specification with the 5?
Right, I will go here because I have a million slides. Let's see. Does it work like this? What is that? Okay, so maybe I will just click many times. This one, you mean?
Yeah. Actually, one before. Is there one before? This one, yeah.
Oh, this one, yes.
If you now replace the send x5
Yes.
with send x4,
Yes.
I think then x will Bob will receive the 5.
Yes. No.
And it's an odd value, so he will send to Z the Boolean value true.
Right, yes.
That's a type error, but even if you would try to send, let's say, -1, the gray thread Dave doesn't exist anymore.
Right.
Because it has immediately exited. So if there were any computation that took a longer time, this wouldn't work. And I'm interested in how you detect such errors. I mean, it's similar probably to the error in the tic-tac-toe.
Okay, so the question is, if here we would send 4, if Alice would send 4 instead of 5, we would enter the else branch, right? And this would be a type error because Bob sends true. But even if Bob would send, a number like we would expect, then Bob does not make a safety violation, and so Bob immediately terminates. But Dave will not actually receive the value because the value would still be in the channel. And the question is, how do we detect these kinds of errors?
Is it a problem at all?
Is it a problem at all? It's a good question. It is in some sense, yes, it is a protocol violation because I would say that part of the protocol would be that you do not just send the value, but you also receive it, at least the way that it was specified here, right? And so, I actually don't know if we would detect this. I think we don't. I think we would not detect this.
Okay, thank you.
Yeah, okay, great. No, thank you. Thank you.
Okay, yeah.
I have two questions, is it okay? One is about the performance. I would like to know, for instance, the overhead of sending 1 million messages and doing nothing about it, just measure the overhead over the Clojure channels.
Like the absolute
and doing
overhead.
absolutely nothing other than the loop.
Yes.
To understand why some exercises are twice or 3 times or 4 times slower, and one is just 5% overhead, and one which processes intensively.
Yes.
I would like to know if you did that, and if there is a knowledge of correlation of the heaviness of this closure. The second question is about...
Sorry, can we first, because I need to repeat the question.
Okay. Go ahead.
So the first question is about the overheads, so the person who asked the question makes the observation that, okay, there's quite a difference between 5% and 5 times slower. Did we do any kind of micro benchmarks to see if what is the source of this overhead? Is this sort of
an empty implementation just to...
Yes, an empty implementation just to measure the overhead. I think we did this at some point, but not in a very, let's say, structured way. So I also don't remember exactly. I could not give you the numbers right now. Like it is so much, absolute overhead that we have on top of an empty implementation. But what I can say about the evaluation that we did here. So if you indeed look at these different kinds of charts, there is indeed a correlation between, let's say, the communication intensiveness of these programs and the results that you see here. So in general, of course, the idea is that the more that these threads communicates with each other, the more often we need to check whether or not these communications are okay. And every check, it adds sort of a constant amount of overhead. And so indeed, for these charts in the middle, the communication intensity is relatively low relative to the total computations that you are doing. Whether for the ones on the sides, it is relatively high. Yes.
Okay.
So that is the general pattern. Yes. Question 2.
Question 2. It comes from the previous questioner, which is, could we somehow record how many messages remained in the channels? Because this is interesting if we probably think about message queuing, where we don't want messages to stack over.
Yes.
So this could be something that prevents us from leaving one message at a time that becomes millions if you leave a server running for 24 hours.
Yes.
All the time.
Yes, so in general, I think boundedness, right, or proving that there is a certain bound on the number of messages that you get in your queue. Oh, wait, I need to repeat the question. So the question is, related to boundedness, right? So
yes, if you
can
could know how many remaining messages, or prove that there are no remaining messages after the run.
Yes, so the question is, if we can prove how many remaining messages there are in the channels, then somehow you can generate errors if the number is non-zero, probably, right? And I think that this would work. So in general, finding the upper bound on the number of messages that you could have during the execution, that is quite a complicated problem. But for any fixed point in time, it is, I would say, well, in principle, it is possible, yes, to know just how many messages we have in the channels, because we run it on shared memory, right? So we just have access to the shared memory and we can inspect those data structures. So yes, we could do that. Also at the end to see if all the buffers have emptied. Yes.
Okay, I think we're going to stop there, so you can ask questions live. Just thanks to the speaker one more.